Now we're going to talk about the eccentricity formula, what eccentricity is, and how we can interpret that eccentricity value. The eccentricity formula is found on the front cover of your reference table in the equations box. It's the first one found in that box. Okay, it reads eccentricity equals the distance between the foci divided by the length of the major axis. Let's talk a little bit about what eccentricity is so that we could come up with these values. Eccentricity describes the shape of all ellipses. Now we already know that all orbits are ellipses. What an ellipse is a shape that is defined by the placement of two focal points. We refer to them as two foci. In our sample here are two focal points. You'll notice that the object being orbited, for example the star, is placed at one of these foci, and there's another focal point, F2. It is a point in space, but there's no physical object there. All right. Let's see. Now, not all orbits have the same elliptical shape. Some may be more stretched out, more elongated. Some may be more round and full. Eccentricity, as a calculated value, allows us to describe that exact shape. So let's try it. Here's our formula again. Eccentricity equals the distance between the foci divided by the length of the major axis. Here's our example that will work and plug in the values. Now, we already know about two foci. When we talk about the distance between the foci, then that is the measured value from the center of one focal point to the center of the other. And if you're measuring this yourself, make sure you measure from the center of that big fat dot. All right? In our diagram here, we see that the distance between the foci measures 2 centimeters. Okay, so that would be my value that I plug in on the top part of my equation. Now, the length of the major axis is going to take us from one end of the shape, right here, all the way to the other end of the shape. It's got to travel through the two focal points. If you don't do that, you're going to wind up with a measure that's a little bit too small. So it goes from one end of the shape through the two focal points to the other end. In our example here, that measured value is 8 centimeters. So I'll plug that in on the bottom. Now you'll notice that centimeters over centimeters, whenever we have two units that are the same in the numerator and the denominator, they can cancel each other out. And that would be true whether we're measuring centimeters on a diagram or in real world values in millions of kilometers. You're still going to have millions of kilometers on the top and millions of kilometers on the bottom. They'll cancel each other out. Therefore, eccentricity as a calculated value has no units, and that's important to remember. We do the arithmetic, okay, just to follow through, and this would divide to 0.25. Okay. Now, because the shapes may vary by just a small amount, we want to be able to measure those shapes, so we take out our calculated value 3 places to the right of the decimal, which means to the thousandths place. And so I need another number here. Of course, I'm going to put in a 0, okay, because there would always be zeros behind there, but I need to make sure I write it. So you always are going to take your eccentricity value to the thousandth place. So my value here for the eccentricity of this ellipse is 0.250, no units. All right. Now, what does that really mean? The range of values for eccentricity goes from 0 up to a value of 1. So it's going to be all the decimal values that you can find in between. That's one of the reasons why we want to make sure we're really accurate and take that calculated value to the thousandths. When we have a value that is closer to 0, of course that means the value for eccentricity is smaller. So we would describe those values as less eccentric, and those values that are closer to 1 as being more eccentric. But what does that really mean about the shape of the ellipse? Because that's what we want to get at. Values that are closer to 0 are going, like we have in our sample here, that's a pretty small value, 0.250. Notice the shape. The shape is very, very round and full. That's what's true of values that are closer to 0. The shape becomes round and full. Okay. Whereas those ellipses that have values in eccentricity closer to 1 would have shapes that are more elongated, stretched out. For example, something more like this for an elongated ellipse, or the round and full. I still have two foci, but they're going to be really, really close together. All right? So we've got some descriptions that we could associate in terms of the numerical value as well as the shape that we would see. So let's see if we can evaluate a series of ellipses. Here we have 4 ellipses. Now you'll notice there's only one object that is inside that ellipse. That is the sun, the star, the object that is being orbited. But I could always find that other position for the F2 focal point if needed. Now as we go from left to right across this diagram, the shapes are clearly changing. Okay? The shapes are becoming more stretched out. So I guess we could describe, as we go to the right, increasing elongation of the ellipse. Going along with that, in terms of calculated value, that would also mean increasing eccentricity values. Something that would be closer to the left-hand side might be a value that would be closer to 0, and that to the right would be closer to 1. So that gives you a little bit of a briefing on eccentricity and the eccentricity formula.